Hello, my name is Carol Leibel, and today we're going to examine Gibbs free energy. Now, in chemistry, you learned that energy is the ability to do work. There are two states of energy. Potential energy is stored energy, like the water behind this dam. We don't see it doing any work, but we know that as the water runs through the opening of the dam, it is converted to active energy or kinetic energy, and it can do work. Those moving water molecules, when they hit a turbine, can be converted into electrical energy. While there are two states of energy, we can also talk about the form of energy. Mechanical energy is the energy of an object due to its motion or restrained motion. For example, a book sitting on a shelf, you don't see it moving, but it has mechanical potential energy. For when that book falls, just like the water going through the dam, it can do work. Nuclear energy is the energy contained in the nucleus of an atom and is released during a nuclear reaction. On the sun, there's an incredible amount of nuclear reactions occurring, and the energy that is released from that comes in the form of heat and light, which reaches the Earth and many other places in space. Chemical energy is the energy stored in chemical bonds and released when the bonds are broken or remade. We rely on chemical energy for our own energy in the form of food. Electromagnetic energy is the energy found in electromagnetic waves. Some examples of electromagnetic waves include things like radiant energy or light, X-rays, and radio waves. Now, electric energy is the energy released as the electrons move from point A to point B through a wire. We can use electrical energy to run a fan or an air conditioner. And then heat energy is energy involved in the movement of molecules. Now, heat energy is always associated with one of the other forms of energy. For example, when you rub your hands together, that's mechanical energy, but it does produce heat energy as well. And when you burn a piece of wood, releasing that chemical energy, you also are producing heat energy. Now, we want to examine the laws of thermodynamics. And the first law of thermodynamics is that energy cannot be created or destroyed, only converted from one form of energy to another form. So look at this little cartoon and see if you can detect any energy transformations that are occurring. Well, first off, we see that the guy is walking. And so where is he getting that energy needed for him to walk? Well, it's going to come from the chemical energy found in the food that he consumes. So in this case, we have chemical energy being converted into mechanical energy. We also know that the blade of the lawnmower is moving. So what's the source of that energy? In that case, again, the chemical energy found in the gasoline is being converted into the mechanical energy of making the blade move. And you might be asking yourself, why in the world is the guy even mowing the lawn? And you would say, well, because the grass is long. Why is it long? Well, because the grass has been growing. And the grass grows because light energy is going to be converted through photosynthesis into the chemical energy of carbohydrates. Carbon dioxide and water is converted into the sugars that the plant needs to grow. Now, the second law of thermodynamics is going to take a little bit more explanation and some background. So let's examine this photograph of a car moving. We know that in order for the car to move, we have to have an energy input, and that comes in the form of gasoline. The gasoline is going to be converted into mechanical energy as the car moves. Once we get done with our drive and we go outside and put our hand on the hood, we'll notice that there is indeed heat energy being produced. We also know from the first law of thermodynamics that energy cannot be created or destroyed, and so therefore the energy input has to equal the energy output. But yet, when we look at usable energy, not all of it gets converted into mechanical energy because we have the heat energy being produced. In fact, only 25% of the chemical energy found in the gasoline is actually going to be used to move the car. The rest of it gets converted into unusable energy. So we're going to have a new term, and that is called free energy. Free energy is the energy available to do work. One more time. Free energy is the energy available to do work. And so now we can examine the second law of thermodynamics. In a closed system, and a closed system is one in which energy cannot get in, nor can energy get out, energy transformations will take place. And as we go from one energy transformation to another energy transformation, some of the usable energy gets converted into unusable energy in the form of heat energy. So over time, as these conversions take place, the amount of free energy or usable energy is going to decrease. Now, in order to keep that system organized, it would require an energy input, which there's no energy can't get in. So eventually what's going to happen is that not only is the free energy going to be depleted, but there's going to be an increase in the disorganization of the system. A measurement of a system's disorganization, if you will, is called entropy. So as free energy declines, entropy increases. So the second law of thermodynamics basically boils down to, in a closed system where there's no energy input or energy output from that system, the total amount of free energy is going to decline or decrease, and eventually it's going to be depleted. As that is occurring, the organization of the system is going to increase, or the entropy is going to increase. So here's a nice little picture of what happens with entropy. Here's a beautiful new house, but time goes by and there's no energy put into maintaining this house, and you can see entropy is winning and disorganization is going to prevail. There are implications for diffusion and free energy. Here is a beaker with a couple drops of dye. And over time, we know that we come back 15 minutes, the dye will have diffused throughout the water. It's become more random. It's become more disorganized, if you will. So in looking at this beaker of water, the free energy of the dye has decreased. It's less organized. So all living things need energy. If you are living, you're going to require some sort of energy input. And there will be an energy output. The energy output is always going to be less than the energy input because unusable energy or heat energy is produced. You might ask yourself, where in the world do we get our energy? And you know that as a heterotroph, we get our energy on the food that we consume. But what about something like an autotroph, a plant? We've already mentioned that that's going to come from light energy. When you die, you're no longer going to have or consume food. So if there's no energy input to keep you organized, then entropy is going to take over. Here is a tree that has fallen and it's dead. And you can see that entropy, where there's an increase in the disorganization of that tree. The decomposers are actually using the chemical energy that's left over in the tissues for their own growth and reproduction. So we're going to look at this cute little video that shows you what happens to a bowl of fruit in about 70 days. Now, what's interesting about the little video is that a lot of the fruits and vegetables were essentially dead, if you will, and you saw them decompose. But there were some in which there were tissue that was still alive. On the potato, for instance, over time, that living tissue was able to utilize the energy in the potato and actually grow new plants. So now, as we go through and we examine free energy, we need to understand that there's going to be two parts. We want to look at the bond energy, or the energy formed or released when a chemical reaction takes place. And then we also want to look at that entropy factor. So first, let's look at the bond energy, as I like to call it. During a chemical reaction, bonds are broken and bonds are remade. So, and then if we look at the energy of the reactants will not equal the energy of the products. There's going to be some change in the energy. That energy we like to refer to as the enthalpy of the reactants and the products. And we're going to symbolize it by the letter H. Now, if during this reaction energy is released during the chemical reaction, well then we're going to say that's an exothermic reaction. Okay? And that the products have less energy than the reactants. It's exothermic. Sorry about that. However, if during a chemical reaction energy is absorbed from the environment and it seems to get cooler, then we call that an endothermic reaction. Okay? And again, we are referring to the bond energies. So let's look at another example. We all have heard of methane gas, and that methane gas can be burnt. And let's look at what happens during this process. First off, methane looks like this, CH4, and there are 4 carbon to hydrogen bonds. Each one of those bonds, when they are broken during a chemical reaction, will release 98 kilocalories of energy per mole. And so because there are 4 of those bonds, we're going to release a total of 392 kilocalories of energy per mole. We also know that in order to burn the methane, we're going to need oxygen. And that oxygen has a double bond, and for a balanced equation, we're going to need 2 of those. So breaking that double bond is 116 kilocalories per mole. 2 of them gives us a 232 kilocalories of energy being absorbed to break those bonds. Now, if you add that up, it tells us that in order to break those bonds during this chemical reaction, it's going to require 624 kilocalories per mole. And then we want to look at the products. So the products are going to involve carbon dioxide and water. Now, carbon dioxide looks like this. C double bonded O, and there are 2 of those bonds. Each one has 187 calories. So when you make a molecule of carbon dioxide in this reaction, you're going to release 374 kilocalories of energy. In the case of water, we have 2 oxygen to hydrogen bonds. Each one releases 110 kilocalories of energy per mole when they are formed. And there are 2 of those molecules, so we're now talking about 4 of those bonds. So we're going to release 440 kilocalories of energy per mole when we make water. So the total energy product that we're going to make is 814 kilocalories per mole. So in terms of changing the bond energies, to break the bonds, it's going to take 624 kilocalories. To make the bonds, we're going to release 814 kilocalories. So what we're going to say is we're going to release 190 kilocalories of heat, if you will. And so it's a negative number. And so this is an exothermic reaction. So a decrease in the enthalpy, or a negative number, if you will, is going to be exothermic. So the burning of wood is an exothermic reaction when we're talking about the changes in the bond energies, those that have to be broken and those that are going to be made. An increase in enthalpy is said to be an endothermic reaction. So overall, photosynthesis is an endothermic reaction. It has a positive delta H. Okay, one more time, delta H is referring to the bond energies, or enthalpy. All right, so now a concept of a spontaneous reaction. A spontaneous reaction is a reaction that is energetically favorable. It's one that we go from high energy to low energy, and it's going to occur without any outside energy source. Do not think of a spontaneous reaction as an instantaneous reaction, because they're not the same thing. Spontaneous reactions can take a long time to occur. Below are three pictures of reactions taking place at different rates. The first one is the bursting of a hydrogen balloon. It's occurring very quickly. Then we have the decomposition of hydrogen peroxide with an enzyme called catalase. And that occurs pretty fast. And then we have an iron nail that's being oxidized with oxygen, and that's going to occur at a much, much slower rate. All 3 of these reactions are indeed spontaneous reactions. So keep in your mind, a spontaneous reaction is one that is energetically favorable. It's going from a high energy state to a lower energy state. So now let's consider a beaker of water. If a beaker of water is at this point right here, if we come back in a couple of days, we will see that some of that water has disappeared. And if I ask you where did it go, you would say it evaporated. It went into the atmosphere. It did not require any sort of energy input. It was a spontaneous reaction, if you will. Now, if it's a spontaneous reaction, it has to be absorbing energy from the environment. However, if you think about your chemistry, when we talk about going from a liquid to a gaseous state, instead that requires an energy input. But yet when we talk about evaporation, we're still saying that's spontaneous. So how can it require an energy input and yet be spontaneous? There has to be another factor involved, and that other factor is entropy. So we want to look at now how entropy is a factor in determining free energy. So here's a nice little video that we're going to watch. All right? Okay.
2 simple chemical reactions, the dissolving of salts in water. Here I have ammonium chloride, and I'm going to dissolve that in water. I'm going to do it and measure the temperature change as the salt dissolves. So here's ammonium chloride dissolving, and you'll notice as it dissolves, the temperature drops. The surroundings decrease in temperature. That's because this is an endothermic chemical reaction. As the salt dissolves, it absorbs energy from the surroundings. We're measuring the surroundings, and we see their temperature drop. Now let's look at another salt, calcium chloride. I'll dissolve that in water. And notice as this reaction goes, as this salt dissolves, energy is released. This is an exothermic chemical reaction. Now, both of these chemical reactions, the dissolving of these salts proceeded spontaneously. That is, the natural thing to happen, the natural direction was forward towards dissolving the salts, towards the salts in aqueous solution. But the energy was not a good predictor. One absorbed energy as it proceeded forward. The other released energy as it proceeded forward. So there has to be another thermodynamic parameter that will predict what's the forward direction for chemical reactions. What's the preferred way that chemical reactions will go? We need to find that thermodynamic parameter, and that's the subject of this lesson.
So what we are saying is that in terms of free energy, we have to take into consider changes in enthalpy or bond energies as they're being made and broken. And we also have to take into consideration changes in entropy. So this next little video illustrates how entropy has an effect on changes in free energy.
What we're looking for is a thermodynamic parameter that will predict the direction of physical processes and chemical reactions. We know enthalpy isn't sufficient. Reactions can go with releasing energy and absorbing energy. So we need another parameter. Well, let's look at this physical process. This is a gas, and we're going to let it expand into a vacuum. Now, we know this goes naturally to expand into the vacuum. In fact, we never notice the gas compressing itself back to one side. When this process goes, expanding against a vacuum, no work is done. It's an isothermal process. No heat is absorbed or released. No energy changes. So this process has three thermodynamic parameters: the energy change, the work, and the heat, all zero. There's no indicator among our thermodynamic parameters that this process will even proceed. Nothing changes thermodynamically as far as we can see. So we need another thermodynamic parameter. Since the reverse never occurs, there has to be something, some driving force that makes it go in that direction. Yet it's not energy, heat, or work. Well, it turns out a statistical argument is what we're looking for. And let's consider this situation in a very simple case. Instead of a mole of particles, let's just take two. If I have two particles, and I arrange it so that the sides of the flask are different beakers, there's one way to arrange this system with both of them on this side. If I let the particle fly to the other side, that is, I open the valve, now either particle, the yellow one or the blue one, could have crossed over to the other flask. So there's two equally likely energy states for the one on either side, the equal distribution. Two equally likely, yellow over here or blue over here, states that describe equal distribution. Twice as likely to see this state as both on one side. Now, as you increase the number of particles, the number of ways you can arrange that state where half are on one side and half are on the other increase dramatically. And we can track them because that actually tracks mathematically as binomial coefficients, or we can use a Pascal's triangle to track the number of ways you can arrange the system with equal distribution. The way you do a Pascal's triangle is you take 1 and 1, and then for two particles, you add the two numbers to get the lower number. So essentially there's a 0 here. So I would add 0 and 1 to get 1, 1 and 1 to get 2, and 1 and 0 to get 1. This tells us for two particles what we already know. If you have both on one side, there's one way to do that. If you have one on each side, there's two ways to do that. And essentially, both on the other side, there's one way to do that. So twice as likely to see the one on each side solution. And you can expand the Pascal's triangle easily. Just keep doing that addition. 1 and 0 make 1. 1 and 2 make 3. 2 and 1 make 3. 1 and 0 make 1. So this would be the 3-particle case, the 4-particle case, the 5-particle case, the 6-particle case. Notice by the time I get to 6 particles, there are 20 ways to have the particles 3 on either side. So here are 6 particles, and I've made them distinguishable so we can tell 3 on each side. There's 20 ways to arrange this. And you could go through there. There's only 20. It would take a few minutes, but you could say, well, it could be the green over here or the yellow over here with the brown and the blue. And you could keep going and find all 20 of those arrangements. The point is, though, all those are equally likely, and there's 20 of them versus the one way to have them all on one side. So if you had all these states available to you, one side and 2 on one side and 3 on this side, the most likely case, 20 times more likely, is equally distributed. Now, as you go to more particles, that becomes even more pronounced. You get to just 50 particles, and it's already hundreds of trillions of ways to arrange the particles equally on each side. So 100 trillion times more likely to see them equally distributed as all on one side. That's dramatic for just 50 particles. Imagine going to a mole of particles. If you go up to a mole of particles, this number 2 to the power 10 to the 23rd is astronomically large. In fact, I would call it bigger than astronomically large because this is bigger than the total number of particles in the universe. So it's just astronomically, bigger than astronomically, more likely to find the particles equally distributed between both sides. We call that, in fact, statistical inevitability. If you look at this system every second for 1 million lifetimes, the likely case is the one you'll see. It's this trillions and trillions and trillions of times more likely that you'll see them equally distributed, so that's the likely case you'll see. No one has ever observed them all over on one side. In all human existence and in all our lifetimes, this is still overwhelmingly more likely we'll see equal distribution. So this is actually a measure of the direction that the universe likes to go. That is, the natural progressions of things is towards the most likely arrangement. The most likely arrangement is the one with the most possible ways, the most possible microstates that are all equal. So when we said for 50 particles, there were 100 trillion ways to arrange them equally on both sides, that's 100 trillion possible microstates. That's a lot of ways, a very large number of ways to arrange that particular arrangement. It's the most likely arrangement.
So in point, what this video was trying to make sure you understood is how important the role of entropy is in determining free energy. So one more time, we've got 2 different reactions. We are dissolving calcium chloride, and calcium chloride, when you put it into water, it releases heat energy. So it's an exothermic reaction. Now, in terms of dissolving, remember that we have a crystal and everything is very organized. When you dissolve a salt, the entropy increases quite a bit. So not only is it exothermic, but it makes sense, it's also exergonic in terms of changes in the free energy. But now let's look at the second example. In the second example, we're talking about dissolving ammonium chloride in water. Now, when we dissolve ammonium chloride in water, it becomes cold. So we know that it is indeed endothermic. But again, dissolving a salt in water, we have an increase in entropy. And so not only is it's endothermic, but the crazy part is that it's exergonic because the entropy factor is greater than the enthalpy factor. So now we want to look at how reactions can be spontaneous or exergonic. So we have three situations here, and in all three situations we have a decrease in free energy. And therefore, all three situations we have exergonic reactions. But in the first case, we have a decrease in enthalpy, okay? But we have also an increase in entropy. That meaning there's an increase in disorganization. So overall, delta G is going to be negative as exergonic. In the second situation, we have an increase in enthalpy. So this is like the dissolving of the ammonium chloride. Okay, it's getting colder. It's taking heat from the surrounding. However, the change in entropy is such that we still are going to have a negative G. So the free energy is still going to decrease. And then in the last situation, there is a slight increase in entropy. However, the change in enthalpy, which is negative, is large enough that it's going to outweigh it. And so we still have a change. This is still it's an exergonic reaction, and delta G is still negative. So the way that it's quantified in terms of changes in delta G, changes in the free energy has to take into account the changes in the bond energy, delta H, and the changes in the entropy. And we also take into consideration the temperature. So free energy is quantified by delta H minus the temperature multiplied the changes in the entropy. Now, another way we can calculate it, let's go forward. Another way that we can calculate it is that changes in free energy is equal to the the free energy of the products minus the free energy of the reactants. Delta G, if it delta G, if it releases free energy to its surroundings, is exergonic. And if it absorbs free energy from its surrounding, then it's said to be endergonic. In general, usually exothermic reactions are exergonic, and usually endothermic reactions are also endergonic. However, in the previous example, we have seen there are exceptions to this rule. So here is another way to graphically illustrate this. In this first graph, we're looking at the free energy of the reactants. And after the reaction takes place, here is the free energy of the products. The change is the energy output. And basically then we're looking at delta G. If delta G is less than 0 and negative, then we say that is an exergonic reaction. On the other hand, if we look at the free energy of the reactants and we look at the free energy of the products, and there's been an energy input, then delta G is greater than 0, and it's an endergonic reaction, or energy is required in order to make this reaction go. All right, I just want to make clear one last time. Free energy is the energy available to do work. Changes in free energy must take into account changes in the bond energy of the reactants and the products, and also changes in the entropy of the system as the reaction takes place. All right, so now if you have 2 moles of hydrogen gas and a mole of oxygen gas and you mix them together, nothing happens. But if you were to add a spark to the reaction, wow, kaboom, an explosion will take place. If we look at the terms of changes in free energy, during this reaction, what we'll notice is that delta G is a negative 58 kilocalories per mole. It is an exergonic reaction. So in order for water to be formed, that spark allowed for H2 to become 2 atoms of hydrogen and O2 to break that bond and become 2 atoms of oxygen. And that then would free up the electrons so that new covalent bonds can be made in the form of water. So that energy that had to be added for that reaction to take place is called the energy of activation. Now, an example of an explosive exergonic reaction, of course, is the Hindenburg. And the Hindenburg was a dirigible that was filled with helium gas. It was lighter than air and floated across the Atlantic. When it reached the United States, there was some sort of spark. It interacted with some wires, but at any rate, there was this very reaction take place, and a terrible explosion took place. So the energy of activation then is the energy that is needed to break bonds and to make bonds. Even if a reaction is exergonic, this still requires some energy of activation to take place. So we want to take a little bit of time and talk about how a cell uses energy, or the most common way that energy is being used. The molecule that's used quite often in endergonic and exergonic reactions or chemical reactions is ATP. ATP is composed of things you know about. It's composed of ribose. Ribose is a pentose sugar. It is C how many, H how many, O how many. Come on, I know you know what a pentose sugar is. C5, H10, O5. And it attached to that is the nitrogenous base adenine. And where have you seen that before? You are absolutely correct. This is the same nitrogenous base that's found in DNA and RNA. And attached to this particular carbon right here are 3 phosphate groups. And these phosphate groups, as you'll notice, they all have negative charges. And so these phosphate groups actually repel one another. So the bonds keeping these phosphates together is a very weak bond. And we call it a high energy bond because it's very easy to remove a phosphate and put it onto another molecule. During a reaction in which you take off that phosphate group and ATP becomes ADP, it's going to release 7.3 kilocalories per mole. It is an exergonic reaction. If you turn around and you couple this exergonic reaction with an endergonic reaction, you can get some reactions to go even though energetically they're not favorable. For example, watch this reaction. We have a reaction in which we are going to take glucose and we want to add ammonium to it. Now, in order to do that, that is an endergonic reaction, and it requires 3.4 kilocalories per mole, and it doesn't happen spontaneously. Okay, it requires an energy input. But now watch what happens. Let's suppose that we take glucose and we're going to phosphorylate it. Okay, we're going to take a phosphate from ATP and put it on to glucose. So when we do that, it becomes glucose phosphate. And then we can take glucose phosphate with the ammonium and we can turn around and make or put the ammonium onto the glucose. All right, so the first reaction right there, or the overall reaction, requires 3.4 kilocalories per mole. But when we use ATP, which by removing that phosphate group is 7.3 or releases 7.3 kilocalories per mole, the net reaction of this entire biochemical pathway, if you will, is negative 3.9 kilocalories per mole. And so now it's energetically favorable. We can put the ammonium ion onto glucose. And so overall, it's an exergonic reaction. And so a lot of biochemical pathways will couple an endergonic reaction with an exergonic reaction. And as long as the exergonic reaction has a larger value, then the net reaction or overall reaction will be exergonic. So here's an example of a biochemical pathway: photosynthesis and cell respiration. Photosynthesis requires the change in free energy is a positive 686 kilocalories per mole. Where in the world is that energy going to come from? Well, that energy is going to come from light. So now you have glucose and oxygen. If you oxidize glucose and you turn it into carbon dioxide and water during a very long biochemical pathway, that change in free energy is minus 686 kilocalories per mole. It's just the opposite. But there is enough energy in the release of the oxidation of glucose that we can take ADP and phosphorylate it and turn it into ATP. So in the first half, this is an endergonic reaction and the energy is coming from light. Over here on this side, this is overall an exergonic reaction, and the excess energy is going to be used to phosphorylate ADP and make ATP. So metabolism then is the sum total of all the biochemical reactions that are occurring in the cell. And in general, there's two types. There are catabolic reactions. Catabolic reactions are those reactions that in general break down molecules, and they are exergonic. And then there are anabolic reactions, and anabolic reactions are those chemical reactions that synthesize or make a larger molecule, and they require an energy input or they're endergonic. Here are some examples of how ATP is used in the cell. The first one is in active transport. You have a protein in a membrane, and when you phosphorylate that protein, it has the ability to take molecules and move them across the membrane. Quite often, it will go against a concentration gradient, kind of like putting perfume back into the bottle after you've sprayed it. It goes against the concentration gradient. ATP can also be used in mechanical work. When you put a phosphate onto a particular protein, that protein may become unstable. And when it becomes unstable, it may change shape and it may contract, allowing some sort of movement to take place. ATP is also involved in chemical work. You can, as we just saw with glucose and ammonium, we can turn around and transfer phosphate from one molecule to another, and we may actually join two molecules and make some sort of a product. So here are some examples that are exergonic reactions, or they are changes in free energy in which the free energy is decreased after it takes place. In the first example, we have a girl who is on the top of a slide, and when she's at the top of the slide, she has more free energy, it's less stable, and has a greater work capacity. Now, when she goes down the slide, when she's at the bottom of the slide, there's less free energy, it's more stable, and it's less likely to do work. Here is an exergonic reaction that impacts diffusion. On one side of the membrane over here, we have more molecules. They're more organized, if you will, kind of like the drops of dye in that beaker of water. What happens over time is that there is a likelihood that these molecules are going to move across the membrane in both directions. However, the net movement will be from one side to the other side until equilibrium is reached. When equilibrium is reached, the molecules are going to move across both sides of the membrane at the same rate. In this case here, again, there's more free energy, it's less stable, you're more likely to do work. What we have is a spontaneous reaction in which the molecules are moving from this side over here to that side. And now when we've reached equilibrium, less likely to do work, more stable, less free energy. Here in the third example, we have an example of a catabolic reaction in which a molecule is being broken down into smaller parts. There is a change, delta G is negative, and the products have less free energy, more stable, less likely to do work. All three of these are examples of exergonic reactions. The free energy of the system has been decreasing. And again, spontaneous reactions are energetically favorable. They're reactions that would occur without any energy input. So we want to look at some examples in biology in which changes in free energy have an effect. And we've mentioned this a couple times already, and that is diffusion. If you have a situation in which one side of the membrane you have more molecules, over here you have fewer molecules, what will happen over time is that there's going to be a net movement from the area that's more concentrated to the area that's less concentrated. Now some of the molecules will move back, but at some point in time it'll reach equilibrium, and so therefore the movement going in both directions will be equal. All right, so here's an example of what happens in diffusion. We're going to remove the barrier. Watch what happens with the diffusion of the molecules. We started off with 100 on the left-hand side. You can see molecules are moving in both directions, but the net movement is from the left-hand side to the right-hand side. We're approaching equilibrium. All right, so the gas now expands to fill both containers. We see the numbers oscillate around 50, but it's going to stay around 50, more or less on both sides. So entropy is a driving force in moving things across the membrane. The example that I'd like to talk about, it has to do with moving gases throughout your body. Inside the lungs, in your alveoli, you're going to have more oxygen than you do in the blood. There is this, due to entropy, we have more free energy here in the alveolus than we do in the blood. So there's this net movement of oxygen from the alveolus in your lungs into the bloodstream. On the other hand, the blood is bringing back carbon dioxide. The concentration of carbon dioxide in your blood at the alveolus is greater. So now we see a net movement of carbon dioxide from the bloodstream into your lungs. And it didn't require any sort of energy. It was a spontaneous reaction. It happened by itself. On the other hand, when the blood goes to a body cell, the blood has more oxygen than the body cell does. Again, we see the movement of oxygen from a higher concentration, more organized, to an area of lesser concentration. This is an exergonic reaction, if you will. Okay, a change in free energy from high to low. On the other hand, you have more carbon dioxide in the body cell than in the blood. So now we see a movement of the carbon dioxide from the body cell into the blood. Another example where Entropy has an effect in the movement of molecules is in your excretory system and the kidney in the filtering unit called the nephron. As you can see by this diagram, many of the molecules move across the membrane, across the nephron through passive transport. That includes salt, it includes water, and if they showed you up here, it would also include other sorts of molecules as we looked at other parts of the nephron. But again, the nephron is this filtering unit that cleanses the blood and is able to move things into and out of the nephron in the formation of urine in the excretory system. Now, at a larger scale, we can look at entropy and how it affects an ecosystem. You have heard of the 10% rule when you studied ecology, and we know that in general, energy from any tropic level that only 10% of the energy from any tropic level can move on to the next tropic level. So in this case here, if the producers contained 1,000 kilocalories, the amount of free energy that will move to the next level is only 10% of that, or 100 kilocalories. And the next level is 10% of that, or 10 kilocalories. And then to the next level, it's only 1 kilocalorie when you get up to the tertiary consumers. That kind of explains why there are so few tertiary consumers. So the second law of thermodynamics is in part responsible for the declining amount of free energy as it's transferred from one tropic level to the next tropic level. I hope that this PowerPoint has helped you in understanding how free energy affects biological systems at all sorts of levels. So I hope to see you next time, and you take care and you have a great day. Bye.